Okay, guys, the first 3 pages of these notes are review. There's just so much going on here in Chapter 6, specifically in Section 6.3, that I thought it'd be good to throw some review in here. So if you feel very confident with what's going on in Chapter 6 and Section 6.3, you can skip the 2 videos that say they are review and go to the 3rd video, which is the notes starting on page 4. If you think it's a good idea to go over this and make sure you know what you're talking about, stick with me here. And if you would like to hear something stupid, I just thought I was making a video for these 2 pages of notes and looked at my phone and realized instead of hitting record for a video, I hit to take a single picture, and then I proceeded to talk through 2 pages of this to myself and didn't record it. And now I hate myself. I hate myself a lot. Like a lot. Okay, here we go. Review. A random variable from the beginning of the chapter is a variable that takes on only numerical values from some kind of chance process. Okay, in particular, a discrete random variable has a finite and countable number of options. Right? Let me skip down to here. A continuous random variable, on the other hand, has an infinite number of options. Okay, those are the definitions. The author gives us a little bit of help when we're trying to decide if something is discrete or continuous. It says, are you counting things? If you're counting things, you probably have a discrete random variable. Or are you measuring things? If you're measuring things, you have choices for how many decimal places you would like to go. And generally, you're probably using a continuous random variable. The easiest option for me to explain a continuous random variable is pick any real number between 0 and 1. We all know there are an infinite amount of numbers between 0 and 1. A discrete random variable's probability distribution is very different for us from a continuous random variable's probability distribution. Since they're countable, I can list them, and I put them in a chart, and I put the probabilities underneath them. For the continuous random variable, they are not countable, so they are not listable. So what do? I represent the situation with a density curve, right? Don't the probabilities all have to have a sum of 1? All of the probability adds up to 1. Well, we could have a density curve that is a uniform distribution in shape, right? In shape. Or we could have a density curve where the shape is skewed right or left. I'm not going to draw both of them. Or we could have a density curve where the distribution it has a shape that is symmetric. So I can't list all the x's. I just contain an infinite amount on a number line, like the amount of numbers between 0 and 1, underneath the curve where the area is 1, and I represent the added up area equaling 1 that way. Now, specifically, this one is back to discrete. After we talked about that, we went to a specific kind of discrete random variable. A binomial random variable is a discrete variable whose values take on numbers of successes. Now, it's no longer just a numerical value of a chance process, which is the definition up here. Now we're actually keeping track of the number of successes from a binomial setting that goes B, N, and P with the following 4 characteristics. Check your bins, people. Each time you go through this chance process, it should be a success or failure, making it binary. They should be independent trials, so the probability of one doesn't affect the probability of the other. There should be a set number of trials, and the probability of success, which we use in formulas as P, should be the same thing for each time we do the event. Okay, I'm going to go to page 2, and I should probably check to make sure I'm actually doing a video instead of just taking a picture of my blank notes like a moron. Okay, we're at 4 minutes, 17 seconds. I like it. Second page. For the next few examples, we're going to use a binomial setting 10, 0.25 to represent the following scenario. There is a 25% chance on every single day for the next 10 school days that it's going to snow. All right, find the probability that x equals 3. This is all review now. So I'm going to do probability that x equals 3 with the binomial formula. I'm also going to do the probability that x equals 3 with a binomial PDF on the calculator. So you see both of these. Okay, it would go 10 days, choose 3, times the probability of success 0.25 to the third and the probability of failure 0.75 to the 7th. Okay, that's the actual binomial probability formula. And then you got to know what this 10 choose 3 means. It means 10 factorial over 10 minus 3 is 7 factorial, and then there's the 3 factorial. Those two numbers on the bottom should always be the same two that are used as exponents. Not in the same order necessarily, but you see what I mean. And then, of course, this is 0.25 to the 3rd and 0.75 to the 7th. They should add up to 10. 3 successes, 7 failures. That should add up to how many things we're doing. Then I'm going to go 10 times 9 times 8, and I stop. I don't write anything else in the numerator because the rest, 7, 6, 5, 4, 3, 2, 1, will cancel with this 7, 6, 5, 4, 3, 2, 1, so I don't need to write it. I will write 3 times 2 times 1 down here. And this 3 and this 2 are going to cancel with this 9 and this 8 for me. So this becomes a 3 and this becomes a 4. It's hard to read my writing, but there's 1s now in the denominator. 3 times 4 is 12, and 12 times 10 is 120. So this ends up being 120 times 0.25 to the 3 times 0.75 to the 7. And when I put that in my calculator, I round it to 4 decimal places, and I get 0.2503. Okay, then there's a big fat or here. I could either use the formula or I could use a binomial PDF. Now your job as an AP statistics student is to be able to do either one of these, because multiple choice questions won't just ask for the answer. They'll ask for, hey, which setup here looks to be right? And if you don't know how to do 10 choose 3 to the factorials to the number, you're going to get the multiple choice question wrong, even if you know how to do this. You see what I mean? So I put this in the calculator, and I round it to 4 decimal places, and I do get 0.2503. Okay, if you forgot how, let me do this real quick. I go second and variables to the distribution menu right there, and then I go down until I find binomial PDF. And in there I put 10 trials, 0.25 for the probability, 3 for the number I'm looking for, and 0.25028 rounds to 0.2503. Okay? So this review example goes all the way down to here. Second time I've done this today, even though the first time I just took a picture of my blank notes like a moron. Hate myself a lot. To find the probability that it snows for more than 5 of the next 10 school days. So this goes like this. Probability that X is greater than 5. Okay, you could find the probability of 6, 7, 8, 9, and 10 as binomial PDFs and then add them all up if you wanted to. Or you could use the CDF. So look, I'm just going to write the possible X's. I'm not going to put the whole chart. But look, X could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I do recommend that the first few times you try this trick, you write them all down so visually you can't screw it up. Greater than 5 means these. 6, 7, 8, 9, and 10. Now you guys know that all of the probabilities underneath here, they have to add up to 1. Okay, so here's what I'm going to do. I'm going to take the 1 that they all add up to, and I'm going to subtract off 0 through 5, because the binomial CDF in the calculator starts at 0 and goes up, unfortunately. It won't start at 6 and go up. So I go 1 for the total they're supposed to add up to, and then I go binomial CDF of 10, 0.25, and then the third number is always the hardest one to get right. But if you draw this out, I got to go up to 5 because I want to get rid of 0 through 5 so that I get the probability for 6, 7, 8, 9, and 10. I'm taking these 0 through 5 right here and subtracting from 1, leaving me that. So back to the calculator. I go 1 minus, I hit second and variables again, and I go, oh, son of a, there we go. I go down till I get to binomial CDF, 10 trials, 0.25, and 5. When I hit enter, I get 0.0197. 0.0197. Okay, let me interpret that probability for you without writing the whole thing down. That is the probability that if it is actually 25% chance that it snows on every day for 10 days, that's the probability that it would snow for 6 or more days. 0.0197. Let me say it one more time. If the probability is 25% chance that it snows every single day for the next 10 days, that's the probability that it snows 6 or more days, 6, 7, 8, 9, or 10. Now, a reminder, what's our cutoff percentage again? For this kind of conversation, it's 5%. And this is lower than 5%. So that means this situation is weird. If there's less than a 5% chance of something happening, and it actually happens, that means it's weird. Okay, so if it snows for 6, 7, 8, 9, or 10 days, because of the probability being less than 5% of that actually happening, so it would be very strange if any of these happened. That's weird enough for us to say it's weird. Something's up. Either it was just a really weird circumstance, or that's not actually true. They said it was going to be true, but the weatherman got it wrong, and it wasn't actually true. It didn't end up being true. Okay, so better said, the fact that it snowed that many days is actually convincing evidence that the probability of snow equaling 0.25 isn't actually true. The fact that something that weird we're saying actually happened because hey, what's the probability? It's greater than 5. If that actually happened, it would be weird enough for us to say, I don't think that's true. That's that conversation. I know you guys hate that conversation, but that's how it goes. All right, let's go to video number 2.